I will see.
Oh, it's granola.
All right, so it's recording, I think. Yes.
Let me type the slides. So probably you can see the slides as well now.
Yeah.
Can you just try to raise your hand? I just can see that way how if I can see it.
Raise my hand. How do I do this?
There should be an option.
Let me see.
Yeah. I can see now.
I don't see the option.
But
I don't think I can raise my hand.
Yeah, but I can see others are raising their hands. And thanks for the.
Okay. Yeah, I don't have this option. Where is it?
It should be, maybe they can write in the chat.
It doesn't matter. It's okay.
Yeah.
So do you want to take questions in the end, or how do you want to do this?
So it's fine if they if you interrupt me in between, but that's also okay. And also I'll have breaks, like there are 2 breaks in between and then the final one. So they will be, because I don't think going continuously for 2 hours is a good idea.
Okay, then I'll leave it up to you. You decide what you want to do.
Yeah, so feel free to ask to others. Like I'll be happy to answer in between as well, and then we'll take break after each section.
Okay.
Okay. So how many?
So let me just introduce you. Hello, everyone. Welcome to the Advanced NMR workshop. Our instructor today will be Dr. Sheetal Jain from UCSB. He's a postdoctoral fellow at the UCSB in the lab of Professor Songyi Han. Sheetal is an expert in NMR, solid state NMR, which makes sense. I'm looking at his CV, and he's been playing with magnets for a while. Sheetal got his PhD, his BS and MS in physics from the India Institute of Science, Education and Research. Then he moved to Denmark, where he did his PhD in nanoscience at the Aarhus University. I'm not sure whether I pronounced this right. Then after his PhD, he spent a couple of years at MIT as a postdoc at the Francis Bitter Magnetic Lab. And from there, he moved to UCSB, to Professor Han's laboratory. So it's a real pleasure, Sheetal, to have you give this workshop, and you can start whenever you're ready.
Thanks. Thank you for the introduction, Stavros. And can you see the full screen now?
Yes.
Yeah, and I want to make sure that I see the participants and everything is, yeah, it looks good. So probably we can start now. Okay, so as we discussed, you can ask me questions during the talk, raise your hand, or we are not that many, so you can unmute yourself and ask question. That will work. And there will be 2 breaks in between after each section, as I will mention in a minute to you. And during those breaks also you can ask me the question. Okay, so the topic today is solid state NMR spectroscopy, and it's mainly I'll discuss about how we can use this for catalytic material characterization. So first question is, why do we need NMR? Well, now it's well known that the technique is really powerful, specifically because it can directly probe a large number of elements from periodic table. So here you can see that except for these magenta ones, all the other elements are NMR active. They have at least one isotope that is NMR active, and some of them have more than one isotopes. For example, nitrogen has nitrogen 14 as well as nitrogen 15. Both are NMR active isotopes, and both can provide different kind of information as well. We can get atomically resolved information from NMR. So here I'm showing a cartoon that if you have a catalytic active compound and if you want to see the details of the catalytically active sites, then NMR can provide you, based on its chemical shift resolution, the local structure as well as dynamics in a broad range, using the different interactions that I'll cover briefly today, that can provide you the details of the structure as well as the dynamics, which are crucial in their catalytic activity. And a good thing about the technique is it does not require your sample to be crystalline. In fact, there are methods now that allow you to study the system in operando condition. So those features make this technique really attractive for catalytic compound characterization. Okay, so today's talk, I have 3 sections. In the first section, I'll cover the brief introduction. It's really broad and very basic thing. And then chemical shift interaction, which we are currently using in a CCEI project. So I'll go into little details how this interaction provide information. And then we'll take a break here. After that, we'll cover dipolar coupling. And in this case, we'll cover dipolar coupling Hamiltonian. And there is a concept of recoupling. And then there are a few examples of different sequences. And then we'll take a break again. And after that, after the break, I'll go into dynamic nuclear polarization, which is a new, well, the technique wise, it's not new, but it's gaining a lot of attention now because of some technical advancements that it can provide, improve the sensitivity of NMR, and that is very crucial for such characterization. And in the end, I'll talk about homonuclear dipolar decoupling, which is slightly different from the heteronuclear version, and then go into the correlation spectroscopy. And if time permits, I'll cover double quantum, single quantum correlation spectroscopy. That depends how long it takes. So feel free to ask questions. I didn't make that many slides. I didn't time it, so I don't know how long will it take, but if we can finish it before time, that's not a problem. We can discuss questions, or we can, but if it takes longer time, then I'll stop without covering the last section. Okay, so NMR, well, it's as I said, really basic introduction is that the technique is based on the intrinsic properties of nucleons, namely neutrons and protons, that they have spin angular momentum. And that means that whenever they are exposed to an external magnetic field, they tend to align to it and start precessing around it. And the frequency of precision depends on the strength of the external magnetic field, but also on the internal properties of the spin. For example, gyromagnetic ratio, which is does anyone has questions? Okay, so for example, the gyromagnetic ratio, which depends on the NMR active isotope. And Stavros, do you see this slider here on the screen?
Yes, I do. You mean the animation?
Not the animation. Oh, okay. This is from, okay, probably this got, okay, fine. So in that case, so the gyromagnetic ratio will, it depends on the isotope. For example, here protons have 4 times higher gyromagnetic ratio. That means their precision frequency is 4 times faster than the carbons. So this directly tells you some information about the element. But moreover, the frequency is also contains the information on the internal interactions. And those internal interactions contain the information of the structure and dynamics, and which we will cover later. But basically, the frequency here contains all the information, and the task of NMR is to record that frequency, interpret it properly, and get the information. So here is another picture, and here basically this is quantum mechanical picture. In this case, we see that the energy levels get split, and this is in the case of spin half nuclei, the lower energy level and the upper energy level in the presence of external magnetic field. And obviously, if there are two energy levels with different energy, their populations will be different. The lower will be slightly higher populated, and the upper will be less populated. The population difference depends on the gap between the two energy levels, and that depends on the external magnetic field as well as the internal interactions. And we can irradiate radio frequencies which are on resonance for this energy gap. And we can express the energy in terms of frequency. So basically the frequency of radio frequency, these radio frequency pulses should be the same as the frequency of this transition. And that would lead to creation of some coherences that will give us the signal, and that signal will have the information. So the internal interactions therefore are critical, and if you want to understand or interpret NMR spectra, it's important to have some basic understanding of these internal interactions. So usually those are expressed in terms of their Hamiltonian, and here I wrote HNMR, which is the complete NMR Hamiltonian. The first term is Zeeman term, which is basically the external magnetic field, and it's a largest interaction, which can go, like for example, 400 megahertz. That's the 400 megahertz for proton Zeeman splitting. The next one is chemical shift, which is sensitive to the coordination number, the bonding atoms, the symmetry and dynamics, and we will cover this in this tutorial. And then the next two are the dipolar coupling interactions, which are spin-spin interactions that depend on the relative distance and orientations of the different nuclear spins. And that is very heavily used in a lot of studies, including catalytic material studies. The next one is J coupling, which is more important in solution state NMR, but can be used in solid state NMR as well, and we will not cover this part today. But basically, this is a isotropic coupling between two nuclear spins. Those are connected through covalent bond. And the last one is quadrupolar interaction, and again, that we cannot cover today due to the time restriction, but it's one of the most strong interactions, and that can make the spectroscopy slightly complicated. On the other hand, it's full of information. It's very sensitive to symmetry and dynamics. The quadrupolar interaction is present only if the spin quantum number is more than half. Okay, so let's start with the chemical shift. So the chemical shift basically is an effect of nearby electron density on the nuclear site. Because when you put the nuclear site into an external magnetic field, the nuclear spin doesn't exactly feel the same magnetic field, because the nearby electron spins induce an extra magnetic field nearby such that the effective field changes. And intuitively, one would think that the electron should create a negative magnetic field, that is the field in the opposite direction of the external field, and the effective field should be slightly less than what we apply. But in practice, it's a tensor, and we will not go into the quantum mechanical detail of how you derive the tensor, but you can imagine that it's not only changing the magnitude of the magnetic field, but also its direction, and that depends on how the surrounding electron density is to the nuclear spin. And then the tensor can be described by the three principal components. And usually in NMR, we use de-shielding tensor instead of shielding, which is basically the opposite of this shielding effect. Shielding effect means the electron shield from the external magnetic field. So the net magnetic field is less, but the convention is to see the negative of that. So you can see here that if all the three principal components of this tensor are same, then basically it's an isotropic chemical shift, which actually will mean that you have a net magnetic field created by the electron spins either parallel or anti-parallel to the external field. That would just modify the magnitude of the main magnetic field. But it can be an axially symmetric tensor. In that case, it's symmetric in two dimensions. Two of the dimensions, the effect is same, but the third one is different. And we will see its effect on the chemical shift spectrum and pattern. But that basically mathematically implies that out of three principal components, two are same and the third one is different. And then the third case could be completely asymmetric chemical shift tensor. In this case, all three are different. All three principal components are different. So before we go into the detail, there is a chemical shift convention, and there are two commonly used conventions for NMR. So basically, instead of expressing the chemical shift tensor in these three principal components, we choose a different set of bases, just a combination of these three, but three different quantities, because those are more intuitive in terms of their physical interpretation. So first part is delta isotropic, which is the isotropic chemical shift. That is the average of the three, and this is Haberland convention. And in this talk, I will use this convention because the simulation software that I use, Simpson, uses this convention. So the isotropic chemical shift is basically average of the three principal components. The anisotropic quantity, which is chemical shift anisotropy, is defined as the difference of this isotropic chemical shift with respect to the shortest of the three components. The three components are defined in this way. This is the convention, that which one is you will call delta 33, which one will be delta 22. That's based on this. And then there is an asymmetry parameter, which is basically the difference of the two remaining components. And if these two are zero, you see the asymmetry parameter will be zero, as I briefly talked in the last slide. The other convention is Hertzfeld-Burzer convention. In this case, the isotropic is defined in the same fashion, but instead of defining this anisotropy and asymmetry parameter, there are span and skew. And these also contain the similar information. There is one more convention that the chemical shift, and probably all of you are familiar with it, is usually expressed in parts per million instead of hertz like other NMR interactions. And the reason for that is this way you make sure that the ppm scale is independent of the external magnetic field, because you know that from the expression that the strength of the chemical shift is dependent on the external magnetic field, and that will cause some problem in interpreting the data. Okay, so now let's go into slight more detail. What does this anisotropy exactly mean? So suppose there is a phosphorus site and it's bound to three silicon spins through PiOS bond. And I did some simulations assuming that the three parameters that are needed for the description of a chemical shift tensor are listed here, that its an isotropic peak is at minus 43 ppm, anisotropic peak is at minus 190, anisotropy is minus 190 ppm, and it's perfectly actually symmetric tensor, suppose. In that case, if you have the single crystal, which is aligned parallel to the main magnetic field, then you will get a peak somewhere around minus 240 ppm, which is none of these numbers, but it comes from the combination of these. Then if you start rotating it with respect to the external magnetic field, for example, 30 degrees, 60 degrees, or 90 degrees, the peak positions shift accordingly. So you can see that the peaks of different orientation can span, in this case, as long as almost 350 ppm range, or 300 ppm range. And the range depends on how large is the anisotropy and how big is the asymmetry parameter. right? Now, in practice, we will have a sample that will contain all of those crystallite orientations, which is basically powder sample. And in this case, if we record a static NMR spectra, then the spectrum will look something like this, shown in purple here. This basically is an average effect of all the possible orientations. And here in this feature, we can see that the delta 33 is this position, and both delta 11 and delta 22 are same, therefore both are here. Now one can ask that why is this not uniformly distributed over all the frequencies when we are taking all the orientations uniformly, when we are assuming that all the orientations are uniformly distributed. And the reason for that is, if you look into the crystallite orientations, the poles are usually less populated than the equator because of the geometry in this case. And that reflects in this, that when you are at in parallel to the pole, your intensity is less, and when you are at equator, then you get more intense peak because there are simply more crystallite orientation in this direction. Now to see the effect of asymmetry, and this is, I just numerically put some asymmetry parameter in of 0.5. The orange spectrum reflects that the delta 11 and delta 22 are now different from each other, and the pattern become even broader. So this already tells you about the symmetry that is present in the system, as well as how large is the chemical shift anisotropy. Now to interpret this data, this kind of spectrum, we need to know how this is dependent on the crystallite orientation in more detail. And of course, I will not go into the complete mathematics of it, but you can see that Hamiltonian-wise, the chemical shift tensor can be expressed in this form, which is basically an interaction between the angular momentum, spin angular momentum I of the spin, the external magnetic field, and here sigma is the chemical shift tensor. And this can be simplified. This is simply three matrices, and you can multiply these three matrices, and you can simplify this, where there will be one part which is purely dependent on the space, the crystallite orientation, and the remaining part is spin angular momentum, which is affected by the radio frequency pulses. So whatever we do by physical rotation or dynamics or symmetry, only this part gets affected. This part remains intact. And whenever we apply some radio frequency pulses, this part doesn't get affected, but the spin part gets modulated. And this is an important trick that we use in NMR experiments. Now the spatial part is the source of information for us because we are interested in the structural and dynamics. And here I'm directly putting the expression for it. So there is the isotropic part, and then the anisotropic part contains these beta and gamma angles. And the beta and gamma angles are basically defined by the crystallite orientation. So if you define three orientation, alpha, beta, gamma, you can uniquely define one point on the sphere. And the third angle is not that critical, but the two angles, if you change them, then the value of this spatial part of chemical shift anisotropy will change. And usually whenever nuclear spin system evolves under the chemical shift or any NMR interaction, basically what happens is that it acquires the frequency, which is what we detect in this form, and this frequency is this spatial part. So therefore, when we acquire an NMR spectrum and do the powder averaging of it, we have this powder angle dependency and the pattern from where we can extract this information. So this may not be very clear, but let's see through one example what happens. So suppose the system has dynamics. So if you record an NMR, and these are not my simulations, I should mention that I got those simulations from this web page. But basically, if you simulate a powder pattern with static conditions so that the phosphorus site is fully rigid, you get this kind of asymmetric pattern. And the fact that all three are different is reflected because of this eta is not 0. Now, if there is an isotropic tumbling motion start, which means that it's a random motion, not along a particular axis. In that case, as the motion, the frequency of the motion, basically the correlation time, as the frequency of the motion increases, the pattern starts to truncate or shrink. And that's because the powder angles, the dependency on the powder angle starts to average out. And if the tumbling motion is fast enough compared to the total anisotropic pattern, then you end up having only a isotropic peak, which is basically the case in solution state NMR. So here you can see that depending on the broadening and the, which is of course dependent on the external magnetic field as well as the intrinsic properties, the dynamics. So for example, this experiment could be performed by changing the temperature, which would change the dynamics. And that would give you some insight on what kind of dynamics is present in the system. Furthermore, the chemical shift, was there any question? Okay. Furthermore, the chemical shift anisotropy is sensitive to the type of dynamics. For example, if you rotate it about, if you have a restricted motion, for example, rotation about one axis, in that case, you cannot average out completely, and the static pattern will converge into a perfectly axially symmetric pattern. So these kind of informations are available, can be obtained using chemical shift anisotropy. However, usually we would like to make these spectra, since this is a broad pattern, so this is covering say 200 ppm even under fast motion, we would like to have much narrow spectrum because there can be multiple sites present, and these multiple slides can be hidden under one peak, or the interpretation can be difficult. And therefore we need to find a way to completely average out by some kind of rotation, which we can do artificially in lab. So we need to find one axis about which this can completely average out. And luckily there is one axis which we call magic angle. So if we look into this expression of the chemical shift anisotropy, and we see this part which survives under restricted motion, if we rotate such that this part becomes 0, so we choose this external, the rotation axis at an angle 54.7 degree, which is magic angle. In that case, we can completely average out the isotropic part, and we will be left with only the isotropic chemical shift. And so here is an example that this is the powder pattern that I simulated earlier with 190 ppm chemical shift anisotropy. And if we spin around magic angle with 100 kilohertz frequency, you get that the only isotropic peak remains. However, to get this kind of resolution and line narrowing, we need to make sure that the magic angle frequency omega r with which this rotor spins is greater than the anisotropy, which is the span by the which is the measure of this span by the powder pattern. So what happens in between? So here is an example, and this is close to what we see in one of our CCEI projects, that if a pattern is static, and here is, these all are simulated spectra with these principal components. So if there is a static pattern, and if you start spinning with 5 kilohertz, which is much less than the total anisotropy, because this is the spectra are simulated at 800 megahertz, which roughly converts this 190 ppm to 62 kilohertz. So this is less than 62 kilohertz. Then we see the spinning side bands. So these are the side bands located at a distance 5 kilohertz from each other. And there will be one side band at the isotropic position, which is the average of the three components. And the spinning side bands in the slow spinning regime, and slow means relative to the anisotropy, you will see that they roughly follow the powder pattern envelope. If you increase the spinning frequency, then the powder pattern becomes something like this. So the gap between those increased because now they are 20 kilohertz apart from each other. The intensity also increased because you see the net peak area of this whole peak is now distributed in these spinning sidebands. So less number of spinning sidebands means they will have higher peak heights, which is good for sensitivity. And in this case, we still have the powder pattern and we can still interpret the data by fitting these spinning sidebands. On the other hand, we gain in the sensitivity and resolution. If we increase the spinning frequency further, we start to see that the powder pattern start to fade away and the peak intensity start to centered on this isotropic peak only. And now the sidebands are really less intense and they are located 50 kilohertz apart. And number of the sidebands also decrease. And if you increase further, you end up with only the isotropic part. Now, in this case, if you see that we get an isotropic part, but we lost most of the information that was there in the anisotropic interaction. And therefore, the magic angle spinning should be used cautiously, or you can do some kind of recoupling, which I will cover in the second part of today's talk. So let's take a practical example. So this is from CCEI and probably you all have seen this data, but now that you got some context, let's see how to interpret it. So we have a PSPP phosphorus modified zeolite. And then in that phosphorus modification, there can be several possibilities of phosphorus sites inside these zeolites. And in the dry state, when we fully dry the sample by heating it for 12 hours under vacuum conditions, we get the NMR spectrum, something that looks something like this. And from the literature knowledge, we know that the peak, which is here, and sorry, I forgot to mark it, but this is basically the peak at minus 43 ppm that correspond to Q3 site. And these peaks are at 20 kilohertz from this peak, which is the magic angle spinning. So you see that there are magic angle spinning sidebands. And these sidebands, you see that this peak, the sideband is larger than the isotropic peak, which you can imagine that probably is a reflection of the powder pattern. Now, if we expose this sample to water for 1 minute, or air exposed for 1 minute, that would cause some water introduction in the sample, then we get that the peak intensity increase, but this also the sideband pattern, the peak distribution in sidebands change. Now the isotropic peak is more intense than all the sidebands. And in fact, now we can fit those spectra using simulations. So this is the simulation which fits well. So far I was showing you the static pattern as well as the different spectra, different magic angle spinning for this peak. And we can get that this is the anisotropy for the dry state. And when we fit this spectrum, we see that the anisotropy decreased from 190 ppm to 160 ppm. So that tells us that the introduction of water resulted into some kind of increased mobility. Now we don't know the details of it and we can analyze it in more detail, but basically the information is that if the dynamics changes because of air exposure or because of the temperature or because of some change in the spatiation, that would reflect into the chemical shift and isotropic pattern. So with that, I would like to summarize the first part, that the chemical shift and isotropy or the chemical shift interaction is a second rank tensor, and the isotropic chemical shift that we see in solution state NMR is basically the average of the three, because the anisotropic part is averaged out. And then the anisotropic average, the part is sensitive to the dynamics and the structure because it depends on the crystallite orientations. The spinning side bands, even under a magic angle spinning, can be used to extract this information. Now, the chemical shift and interaction contains a lot more information that I did not cover today, and you can search in literature. For example, it has been used in probing the bond state acidity or hydrogen bonding or chemical exchange, and there are plenty of references for that. So I'll take a break here. Please ask questions if you have any, or we'll start in 5 minutes.
I think we have a question from Asif.
Yes.
Yes, please go ahead.
Sheetal, I have a question. So when you do magic angle spinning, you get side bands. And then you also showed the expression for anisotropy. Is it possible to look into that expression and analyze sideband?
Yes.
Okay. Can you please help me with that?
Yeah, so there is actually a theory. So this is a really good question. Right now, I just explained that you can fit these spectra by numerical simulations, but indeed there is a well-established theory of the peak intensity distribution over these sidebands. And that theory is rigorous, but basically you can analytically find a solution that will describe this expression. This powder pattern. So yeah, I think that was the question, if I got it right.
Yes, thank you.
Yeah. Mateus, you're next.
Yes, hi Sheetal. So when you say that in your example, you say, okay, exposure to water brings some mobility to the sites.
Yeah.
But if these sites are still Q3 sites, can you comment on if the sites are not, my point is, if the sites are not changing, how they are...
the dynamic is changing,
Yeah.
Yeah, so yeah, we thought about this, and I cannot claim that the interpretation is right, but what I think is, because these sites are framework bound, and the framework also is sensitive to water. So if the nearby framework gets flexibility because of some water breaking of SiO-Si bonds, converting them to SiOH bond, nearby sites, that would lead to some mobility increase in the bind site. But as I said, we are not sure, and I'd like to take inputs from all of you on that. What could be the reason behind it? But that could be a reason, because you are right. The Q3 site is not, the nature of the site is not changing. It's still Q3, its chemical shift is not changing.
So then you think that, for example, if we are considering the hydrophilic surface of PSPP that has a lot of OH sites, as it gets more hydrated, the OH groups that form on the surface essentially could be changing the that could be changing the bond vibration.
So that's a detailed question, and I'm not sure if it's changing the bond vibration or I think that could be it. But yeah, basically what I'm imagining is that the framework is extremely rigid after completely drying, all tightly bound to each other, and once the water goes in, there are some changes in some new bonds are formed and some bonds are broken, and that lead to some improved flexibility.
I see. Okay, thank you.
Okay, so if
can I actually make a comment briefly?
Yeah.
Yes, Songy. About the question, even though we don't know what the mode of the dynamic is, we can say it's not vibration because roughly the type of frequency that is involved in that. So it's more like rotational and translational motion that we're talking about. Most likely not vibrational dynamics.
Yeah. Okay. So with that, now let's go to the next section. And in this, we'll talk about the dipolar coupling, which is another important interaction in solid-state NMR. So basically, a dipolar coupling is an interaction between two spins. And here I'm depicting them as I and S. And you can imagine the two spins as two magnetic dipoles. And when two magnetic dipoles interact, the expression is given here. And we can always express this magnetic moment in the terms of spin angular momentum, gamma I. And this R is a vector in a 3D space. And that can be expressed in theta, phi, and the distance between the two, R, theta, phi. And if we do that, then we get, this is a complicated expression for dipolar coupling Hamiltonian. And we'll go into the most important part of this dipolar coupling Hamiltonian. But basically what happens is that in presence of main magnetic field, most of these terms are not effective. And the reason for that is the term, those are not parallel to main magnetic field, which is IZ. So for example, the term here has S plus, which is not parallel to IZ or SZ. The term here are both not parallel to IZ and SZ. These terms will get cancelled in presence of the large magnetic field. So the only terms that are parallel to the main magnetic field, those will survive in under the experimental condition, and those will show up their impact on the spectrum. The spectrum get even more, the Hamiltonian get even more simplified in case of heteronuclear spins. So if the spins that are coupled belong to, say, proton and carbon or proton and phosphorus, then their Lama frequencies are too different from each other. And in this case, this term is also averaged out. And therefore, the Hamiltonian becomes really simplified and has this form, which has a spatial part that I'll go into detail, and a tensor. And the tensor is expressed in this form, where you have IZSG as well as this zero quantum term, which comes from homonuclear case. And because in that case, both the spins I and S have very similar Lama frequency, and then both I and S will modulate with similar frequency, and then you have a static term. But in heteronuclear case, the Hamiltonian is only this 2IGSG, the spin part. So let's look into this final expression of the Hamiltonian, and you can see that there is again a spatial part and a spin part. And the spin part depends on whether it's heteronuclear or homonuclear. But the information contained is in the spatial part. You can see that the R is the distance between the two coupled spins, and theta is the angle between the vector that is joining the two spins and the external magnetic field. And again, we can see the effect of magic angle spinning on this tensor. And here we need to go into slight more detail, because usually we would require to recouple this Hamiltonian. So that will come into the next slide. But we need to see that in presence of spinning, what happens is that this Hamiltonian breaks into the 5 different terms, and one of them is 0. So basically, let's simplify it. Let's try to look into it slightly more detail. What happens is in presence of external magnetic field, you can imagine that the tensor, the component of the tensor which is parallel to this axis will have 0 component contribution. That's because of this fact, because anything that is aligned to this, which satisfies this condition, will be 0. Anything which is perpendicular to that, and you can break all the vectors in that fashion, will have a spinning, because you are spinning around this axis. And because of the spinning, that will average out. That's a vector model, but in principle, this is a tensor, and therefore there will be 5 components instead of 3. And the 5 components will have 2 types of frequencies. The 2 will modulate with omega r, the frequency of the rotor. So here m can be +1 and -1. And the another 2 will have frequency 2 or -2 omega r, twice the frequency of the rotor. And why these details are important will become clear in the next slide, but basically these components still contain the B, which is the distance information and the crystallite orientations in there. So what happens is that when you start modulating, the components will modulate like this with omega r frequency, and you see that in average it's 0. So that's how you average out the anisotropy. The other component that are modulating with twice the frequency, they also lead to 0 contribution on average. This is basically a rotor event. So you start spinning here, and after one rotor period, after one spinning of the rotor, you get here and you take the average of that. So now how do we get the information out? Because the resolution is improved, but the information that was in there, the distance as well as the angle, is gone because of this averaging. So we had to look back into our Hamiltonian. So this part that makes it 0, because average of this e to the power I m omega rt is 0, because this is a perfectly sinusoidal or cosine modulation, which in average give you 0. But now we can play our tricks with the spin part. And I mentioned earlier that when we use radio frequency pulses, we can modulate the spin part without touching the spatial part. So if you, for example, put a pi pulse basically inverts the sign. It's 180-degree rotation of both the, on I channel. If you put, then it will flip only the I channel, and that will result into this. So the Hamiltonian will change its sign. Now we can use this trick. For example, m equal to 1 components are modulating with omega r frequency. So now if you put a pi pulse in the middle of the rotor period, then the Hamiltonian will flip sign from this to this. And that would result into a non-zero average Hamiltonian. And that's how you recouple the only omega equal to +1 and -1 part. Of course, this will scale down because the averaging is not fully recoupling, but it will be proportional to this. Similarly, if you want to recouple m equal to 2 components, that means the components that are modulating with twice the frequency, you can put a rotor, your pi pulses at 1/4 of the rotor period. And that would again result into a non-zero static Hamiltonian. You can see that you can either choose m equal to 1 or m equal to 2 components. And usually we prefer m equal to 1 components. That's not always the case, but in most of the cases, because this has square root 2 higher in magnitude. And this comes from the powder averaging and the calculation. But that's the important information that we have. And based on this, I'll give you one example where the experiment exactly uses this trick. And probably you have heard the name of the experiment known as REDOR. Basically, it's a heteronuclear recoupling pulse sequence that puts pi pulses at every half a rotor period. So you start the excitation on the I channel and then recouple the Hamiltonian using these pi pulses. And you can see that it doesn't matter whether you put pi pulse on this channel or that channel, as long as it's only on one channel, because if you put pi pulses on both the channels, you can imagine that both spins will change sign. That would result into the same Hamiltonian. That means it will not be recoupled. But once on I or once on S will lead to recoupling. And that's how the pulse sequence is implemented. Now you can ask, why did you choose one pulse on the another channel? And there is a practical reason behind it, because then this way you also refocus the chemical shift, isotropic chemical shift. This is a trick we commonly use in solution state NMR as well. That if you put pi pulse in the middle of the evolution period, then the chemical shift during this period cancel out the evolution chemical shift during this period. And that makes the spectrum, the REDOR interpretation simpler. So without going into the mathematical detail, because we now have an intuitive idea what's going on, in this Hamiltonian has an average part this and the spin part this after this, under this REDOR pulse sequence. So basically this is the frequency, the spatial part that is going to be encoded in our signal. And you see that this frequency contains B and gamma and beta. So B is the distance information because it's proportional to 1 over r cube, as I showed in the previous slide. So our state, the spins, which we create Ix here, they evolve under this Hamiltonian for this period during the readout, and it goes into Ix, acquires a frequency, and then converts into this part. So basically, this frequency is encoded in our signal. And of course, this requires powder averaging because it depends on beta and gamma. So let's see how do we extract this information out in readout. So here is a more practical version of the pulse sequence that we use. Basically, what we do is we repeat this readout block n times, and n is a flexible number. So we use n equal to 1, 2, 3, 4, and that means we vary the mixing time. We call it a mixing time for how long the readout or for how long the heteronuclear Hamiltonian is active. We modulate that, and that modulation will allow the evolution of the dipolar Hamiltonian. So for example, there is a carbon and nitrogen spins coupled with each other. And if we vary their coupling strength, B, so suppose 500 Hertz, that means it's a long distance. And if the coupling becomes stronger, that means it's a short distance. So if the distance between the two is changing. And then we record the readout spectrum. So basically these points are recorded by changing each point represent 1n. So that's basically changing the mixing time. And then we record the same data set without these pi pulses for a reference. And we calculate this factor. Then we calculate this factor and we plot that. And this is called the readout curve. And this readout curve, and in this case it's simulated, but this readout curve can be fitted using simulations or analytical expressions. And that would give you the dipolar coupling strength, B. And that dipolar coupling strength, B, will give you the precise distance between the two. And this precision can be sub-angstrom distance, precision. So that's how the readout is used. And I don't have a practical example because I wanted to cover CP in this talk because that's what we use. But you can imagine to use this kind of experiment for measuring distances between, say, silica and aluminum or phosphorus aluminum. There are practical examples that exist. Now let's go into another kind of dipolar recoupling, which is more commonly used. And this is probably the most common NMR pulse sequence used in MAS NMR. And this is recouples, but this also transfers the polarization. And this is known as CP. So the basic idea now is that, again, here is the dipolar coupling Hamiltonian of the heteronuclear couplings, heteronuclear spins. And you have a frequency omega r because of the rotor. You are spinning the sample, so a special part is rotating with either 2 omega r or 1 omega r depending on the components. Now suppose you irradiate the RF pulses on both the channels with omega 1i on I channel, omega 1s on S channel, and I and S can be proton and phosphorus, for example. Now you have control over these amplitudes. So you modulate this part with omega I, you modulate this part with omega S. And you can see that now there will be 3 total frequencies in this Hamiltonian. And if you find a condition where the sum of the 3 frequencies is 0, that means the Hamiltonian is no longer getting averaged out. The Hamiltonian averaged out only because it's modulating. And that's why the dipolar coupling is no longer active. But if it's static, it's not modulating anymore, then the dipolar coupling will evolve and have its effect on the system, and it will reflect into the NMR spectrum. So basically, by satisfying this condition, we can transfer the polarization from one spin to another spin. And we can choose the components by choosing m equal to 1 or m equal to 2 condition. Which component? So you can see that this will lead to a faster polarization transfer because this is slightly higher in magnitude. So m equal to 1 components are preferred in CP. Now CP is often used from proton to X could be low gamma spin like phosphorus relatively low gamma spins compared to protons like phosphorus, carbon, silicon, aluminum. And when you do that, then the sensitivity increases because the protons have larger gyromagnetic ratio. So the signal here is more intense, which is now transferred to the less sensitive nuclear spin. And also usually protons are are faster relaxing compared to, for example, phosphorus or silicon. In case of quadrupolar nuclei, that assumption doesn't hold, but still protons can improve the sensitivity. So just to be clear, that the fast relaxation allows us to repeat the experiment fast, because you see every time before starting the experiment, we need to wait for system to come back to equilibrium. And that depends on how fast the system relaxes back. Now, an important note here is that the CP spectrum that we obtain, for example, we obtain the CP spectrum of phosphorus or silicon spins. We cannot use them for quantitative analysis of the quantities of the different kind of species, because the spectrum now is biased by the fact of their proximity to protons. Of course, because strongly coupled will have higher intensity, higher representation in the NMR spectrum than the weakly coupled, or those are not coupled to protons. So here I have one example, and this is not from materials, but you will get the point here, that the same experiment can be used to do heteronuclear correlation spectroscopy, which tells you detail about the system, the structural details about the system. So let's see, there is a model system like this. There are 3 spins of one kind, suppose phosphorus 1, phosphorus 2, phosphorus 3. And there are 2 spins of another kind, suppose silicon 1, silicon 2, something like that. Or proton 1, proton 2, proton 3, and phosphorus 1, phosphorus 2, whatever. There are 2 heteronuclear spins. And if you want to know which one are coupled strongly and which one are coupled weakly, the CP, one-dimensional CP cannot give you that information, because you will simply see peaks from all 3 I spins being transferred to S spin. But what you can do is a 2D version of experiment. So basically you introduce a time T1 here. So first excite the protons or I spin, and then they put a delay, and then do CP and record, and keep changing that delay such that you will get another FID in this dimension. Now you can Fourier transform this into dimension. So the direct dimension, which is this, will contain the chemical shift of the S spin on which you are recording. But there will be an indirect dimension in which you will get peaks that are evolving with the chemical shifts of I. And the cross peaks are the ones, those were evolving under chemical shift of I in this dimension and chemical shift of S in this dimension. And that will only happen if the 2 spins are coupled strongly enough. So, for example, in this case, I3S2 are strongly coupled because they are located close to each other. So then you see that the peak representing I3S2 is relatively strong. So the peak intensity is by this grayscale here. So this is relatively strong compared to a peak between I2 and S2. So if you see I2 and S2, it's really weakly coupled, almost coupling is non-existent, and the peak is almost non-existent there. So such analysis, for example, I2 S1, you can see now, is again strongly coupled, and you see a strong peak here. Furthermore, you can vary this mixing time, and that would result into more intense peaks, because more time you give, more time you have for polarization transfer. So the strongly coupled peaks will become even more stronger, and the peaks that are weakly coupled will start to show up. Now, of course, this all depends on the relaxation times, and there are some other factors, but roughly this is the idea, and this pretty much holds in a reasonable amount of mixing time. So now let's see an example of this kind of spectroscopy. So here the question was, the system was a polyionic liquid, and I was part of this project, so that's why I chose this example, because the data was well processed already on my computer. So, but the point will be clear to you that if we want to know the affinity of a metal cation, lithium in this case, which is important for conductivity in these polyionic liquids, and because those are the candidates for solid electrolytes in battery. This is a crucial information to know that lithium is located near these ligand, imidazole, or near these polymer backbone. So that kind of question can be answered using this heteronuclear correlation spectroscopy. So what we did is first we recorded the proton spectrum that's given here, just by simple direct excitation proton spectrum, and we can assign that these peaks are imidazole peaks and these peaks are from the backbone. And now you can do proton to lithium CP and you get a really sharp lithium 7 peak. So this M is lithium. Now this peak tells you that, okay, lithium is close to some protons, because that's why the CP worked, proton to lithium CP worked. But this cannot tell you which protons. That information is not there in this peak. Whether it's these protons, those are located, those are coming from the imidazole, or whether it's these protons, those are coming from the backbone that is giving rise to this polarization transfer. So to differentiate between the two, we did the heteronuclear correlation spectroscopy like I described in the last slide, and we get a 2D spectrum that is shown here. So now you see that there are peaks in the indirect dimension that correspond to the protons. And then the direct dimension, there is only one peak, basically. This all is one peak, right? That is coming from the lithium. So now if you compare the projection of these contours with the 1D proton peak, you see that in spite of being such a strong backbone peak, in the heteronuclear correlation spectroscopy, almost all of the backbone protons are suppressed. And the imidazole peaks are relatively higher in intensity. So that answers the question that the lithium is most likely located near the imidazole compared to the backbone protons. So these kind of information can be obtained, and you can imagine the application of this method to catalytically active compounds, where, for example, if you want to know the protons that are hydrogen bonded or clustered protons, which may have slightly different chemical shifts, and where they are, how far they are located relative to the framework silicon spins. These kind of experiments can be performed using this heat core correlation spectroscopy. Okay, so now I'll go to another pulse sequence, another version, which we are using in CCEI project, and I'm running a bit slow, so I'll cover it slightly faster, which is respiration CP. And this is pulse sequence wise, it's similar. It transfers the polarization from one spin to another. But the implementation is completely different. Instead of using 2 CW radiation on both the channel, what you do is a phase flip pulses, X and X bar, phase flip pulses on one channel, and a short pulse at the end of a rotor period. So this is a rotor synchronized version, and you repeat this block for your mixing time. In this case, you have a control on mixing time, and in this way, you have a control on your loop. The condition for CP was this, as I mentioned earlier. The condition for respiration CP is that the amplitude of the 2 short pulses should be the same, because you can control them, and the amplitude of the recoupling pulses should be twice the rotor frequency. So if you are spinning, say, 12 kilohertz, then you need to put 24 kilohertz RF amplitude here. And these two you can choose such that both should be the same. So one advantage, and that's a detailed mathematics, but if you want to know why respiration CP usually is more sensitive than the CP, is because in CP you saw earlier, you can choose either M equal to 1 or M equal to 2 components, but mathematical analysis, which I'm not showing here, in respiration CP, you can combine both and you get both the information out. But more important feature of respiration CP that we are interested in this project is that CP gives you the polarization transfer from one spin to all the possible spins nearby, because it's not, if they are all coupled, as long as it's not frequency selective. So for example, if there are 3 phosphorus present, Q1, Q2, Q3 type of phosphorus, all will get polarization enhanced by proton to phosphorus spectrum. But respiration CP, you can choose one of them, and you can selectively detect it with its chemical shift anisotropy pattern. So this will become clear in the example here. So I'm not, so these are the spectra recorded under low temperature condition, and that's because of DNP, and that I'll introduce later. However, DNP doesn't affect the interpretation of these spectra at all. So basically the blue spectrum here is the CP spectrum. And you see in the CP spectrum of this EFPP sample has Q2 and Q3 species, the isotropic peaks, and their spinning sidebands. Now you see the spectrum is crowded. There are so many peaks. And for example, there could be hidden species, for example, Q0 or Q1, that you cannot detect using CP. Also, it's difficult to fit this spectrum and get the chemical shift and isotropy pattern out because you have multiple peaks now of different kind of species. So now if we do the respiration CP targeting at Q3, we get the spectrum that looks like this. So you see the Q2 peak, which was more intense in this case, is suppressed almost completely in respiration CP. Now we can fit this, and we find that there are two peaks that are needed in the Q3 region. These are the chemical shift, isotropic chemical shifts of the two fitted components. And they have their different chemical shift and isotropy. One of them is slightly higher in chemical shift and isotropy, and another one is slightly less. So you can find these kind of detailed information by this selective excitation. Earlier, this peak was not observed in CP because most likely it was hidden under the Q2 peak. Now, this is one information on Q3 that there are at least two sites and there can be more, but basically there are multiple Q2 sites with varying mobility that are present. That kind of information is there. Furthermore, now you can do Q2 selection in the same spectrum. And now you have a spectrum that has mainly the Q2 peaks, and you can fit the spectrum again using the simulations. And you see that in this case, there is the spectrum can be fitted using single component, but the chemical shift falls into Q2 region, and its chemical shift and isotropy is less than both of the Q3 peaks, which makes sense that Q2 should be slightly more mobile compared to the Q3 species. And then you can use the trick again for...
Before you move on, I think Mateus has a question.
Yes.
Yes, I had a question. So just a clarification, actually. When you say that you can target using the respiration CP, that you can target each type of site that you have.
Yeah.
My question is, how do you choose the frequency that you're going to target? Do you use literature reference? Do you do simulation?
Yeah, so basically, if you record as just 1D phosphorus spectrum or a CP spectrum first, then you see what are the peaks there. And if you get assignment of these peaks, then we know the chemical shift of these peaks. So once we know the chemical shift of these peaks, basically the chemical shift is a frequency. So in respiration CP, we choose that. So we, because it's a parameter in NMR experiments, you choose O1P, there is a parameter that decides what frequency your radio frequency will be, radio frequency pulses will be. So we choose those. So in this case, the radio frequency was on this peak, Q2 peak. So you choose O1P to be minus 25 ppm. And then the range of respiration CP is plus minus 2 kilohertz to that frequency. So the peaks that are around plus minus 2 kilohertz of your carrier frequency in NMR will be excited. So that's how we choose it.
I see. So that's why, for example, so you target one frequency for the Q3, for example, but because the other peak is in the nearby frequency, you also see it, essentially.
So if the peaks are located within the range of plus minus 2 kilohertz, then respiration CP can't suppress one of them.
Got it. Okay. Thank you.
But you can go to higher field, and you know, as you go to higher field, the peaks will be more separated, and you can use this trick still.
Yeah. Okay.
So now you see that you can use the same trick in Q0 and Q1. So now you target the Q1 species by putting your carrier frequency at Q1 position, which is minus 11 ppm. or the Q. So then you get the spectral fitting that again require two components. And one of them is in minus 7.5 ppm, which is in Q1 regime. And another one is now in Q3 regime. And that's because there is an intense Q3 peak that is overlapping. And as Matthias asked, there is an overlapping Q3 site that is in the range of respiration CP, and that shows up. Its chemical shift and isotropy falls in the Q3 regime, and its isotropic chemical shift as well. But there is also a tiny amount, at least because the signal to noise ratio of this spectrum is less relative to others. There is a tiny amount of Q1 present in the sample. Now, if you see the Q0, if you try to select the Q0, then you get this nice sideband pattern, but the fitting turns out that it cannot be fitted with any isotropic peak in Q0 regime. You need both the isotropic peaks to be in Q3 regime to fit that. And therefore, that tells you that whatever intensity you are getting at Q0 position is basically a spinning sideband of Q3. There is no Q0 present in the sample. This can be verified, by the way, and that's slightly more detailed and that we did by changing the spinning frequency as well, because by changing the spinning frequency, you know that the spinning sideband position will shift. The spinning sideband position is located at the 7 kilohertz from the isotropic peaks because we are spinning 7 kilohertz. But if you spin 5 kilohertz, these peaks will be at 5 kilohertz from the isotropic peak. So that's another verification that we did. So these kind of information are possible. You get the chemical shift, selective chemical shift and isotropic information out. So basically, to summarize, that dipolar coupling can be used to get internuclear distances like Redor kind of experiments. It can be used for heteronuclear correlation spectroscopy that can give you the structural information. CP also improves your sensitivity. And then you can use more pulse sequences, more advanced pulse sequences like respiration CP to get more specific information out. And I should mention that there are a number of different pulse sequences exist. I chose respiration CP because we are using this in this project, but there are other pulse sequences that have different properties and are suitable for different kind of projects or information, but that can also be used. So this is time for the next break. We already have completed 1 hour.
Yes, Tanu, go ahead.
Sheetal, so I just had a question on the recoupling part. You said that there was an m equals to 1 term and m equals to 2 term. So I was just wondering when specifically you'd use the m equals to 2 term and whether that has to do with relaxation for the recoupling.
Yeah, that's a good question. When you have to choose n equal to 2, When you have to choose n equal to 2, there are very specific examples when you need to do recoupling of n equal to 1 first and then n equal to 2 to verify the result. Sometimes that has been used in literature. It does not, the relaxation rate of the two components are not different because both have same, it's both, basically they are different in the spatial part. They are not different in spin part. Spin part is same in both the cases. So the relaxation properties of the two components are not different. Their amplitudes are different. But for example, if you recouple n equal to 1 part, you will get 1 buildup, and that will have this dependency in modulation. And if you decouple n equal to 2, then you get this, and you can use that to confirm your observation in certain cases. This is specifically used in more advanced double quantum, single quantum experiments that people have used in polymer, in studying polymers. But yeah, I can't tell you the detail in this short time.
Okay, thank you.
Asif?
Can I make a comment here, Sheetal?
Yes.
So you said right that m equal to 2 component is smaller in magnitude. So I have seen some recent paper in literature since that component evolves slower. So if the coupling is too fast and people want to slow down the dipolar evolution, they use m equal to 2 components. So for example, proton carbon, they would prefer m equal to 2 component. But if it is say carbon nitrogen or other smaller coupling, they use m equal to 1 component. So this is something recently I have found.
Yeah, that's really nice comment. Yeah. Yeah. So that answers more directly to Tanma's question. Thanks, Nasir.
Thank you.
Sangi?
I just wanted to maybe have you discuss whether REDOR can be used for silicon phosphorus distance measurement, and whether the limitation why you wouldn't directly use it is just a sensitivity problem, or any other discussion about doing REDOR curve measurement from silicon to phosphorus.
Yeah.
With detecting phosphorus, of course. Because, well, it doesn't have to be phosphorus, but whichever one. Has that been done? Can you use it for the CCEI samples?
Yeah. So, well, that can be done in practice, but in principle, but in practice, there is one problem. The sensitivity is, of course, a problem, but that we can take care of using DNP or something. But in REDOR, we have these delays in between, and the magnetization is in transverse plane. So what happens is during these delays, and if you have weak coupling, so for example, phosphorus silicon POSI coupling is 360 Hertz. So it requires hundreds of microseconds to get the REDOR curve. And during that time, there are chances that your signal relax, because if the sample is heterogeneous, then the relaxation rates are usually fast. So that's a challenge. It can be used in well-defined structures, and I'm pretty sure people have used it. The REDOR and its version for example, they have definitely used it for phosphorus aluminum, because of course both are relatively more sensitive to NMR. Aluminum is quadrupolar, so that requires slightly different version of REDOR, but same principle can be applied there, and it has been used. Yes.
Okay, thank you.
Okay, so now let's go to the last part of the talk. Probably go to, yeah, not here, but here. Yeah, so now in the last part, we will cover the dynamic nuclear polarization. And the reason for that is partially, like Songi asked the question, is sensitivity is a problem? And that definitely is often a problem in NMR. And one way to address that is this rapidly emerging technique, dynamic nuclear polarization. I will not go into the mathematics of the technique, but I'll try to cover how we usually perform these experiments. So the basic idea is that the polarization in an external magnetic field at a given temperature is given by this formula here. And if you plot that, then the protons, those are most sensitive isotopes, NMR active isotopes. And here, even those are significantly less polarized than the electron spins. And that's because of the fact that the gyromagnetic ratio of the electron spins is 658 times more than the gyromagnetic ratio of protons. And therefore, it will be really great if we can find a way to transfer this polarization from these electron spins to nuclear spins, just like we do it in CT. And that will improve the sensitivity of NMR by hundreds of folds. And that will allow us to do several experiments that we can't do because of the practical restrictions of the sensitivity. So for that, what we need is a source of electron spins in the sample. Usually we use these radicals. Those are APR active, nitroxide or carbon-based radicals. Then we need a matrix, glassing matrix, to make sure that these radicals have long relaxation time, and we form nice glass in low temperature, because we need the proton spin network that will be clear in the next slide. So we mix it with the glassing matrix, and we mix these two with the NMR sample. For example, the PSPP sample will be mixed to a tech pole, which is a radical, and then TCE, which is another glass forming solution. And we put that into the rotor, freeze, perform the experiments at liquid nitrogen temperatures around 100 Kelvin, and use microwaves near EPR to transfer the polarization from electron spins to the proton spins. So that, to understand that, here is an animation. Suppose there is an electron spin, which is from your nitroxide, and then there is a glassy matrix of protons that is from the solution that you use, for example, TCE. And then there are the target spins, which are phosphorus located in the pores of the geolite or outside. And then you freeze the sample and start spinning at 7 kilohertz or so, whatever you can spin at 100 Kelvin, and then you irradiate microwaves. So what then that does is transfer the polarization to nearby proton spins, because of the way you choose the frequency of the microwaves. And because those protons are more strongly coupled because of their larger gyromagnetic ratio and their location to the nitroxide radical. But the good thing about the protons is that they form a really nice network. So they have really rapid, relative to any other nuclear spin diffusion rate, which means they distribute their polarization among themselves. And this allows that the polarization travels all the way into the pores, or the distances up to micrometers away from it has been shown up to micrometers away from the location of the radical. And then you use the CP experiment that we showed to transfer this polarization to the target spins that would result into the enhancement of the signal. And if you measure the signal without microwaves and with microwaves, a factor of 100 is commonly achieved at 400 megahertz. It can be more, it can be less, but for factor of 100 would lead to, because the sensitivity is proportional to the square of the signal enhancement. And that means roughly what you get in one day using DNP would take you 27 years without DNP, because that's a 10,000-fold gain in time. So 10,000 days makes you 27.37 years. Okay, so we can use this technique. And for that, here I briefly describe the experimental setup just to tell, because most of you probably have not seen the DNP setup. Basically, it's the standard NMR, but then you have an external gyrotron that allows you these strong microwaves. And then there is a waveguide that goes to the probe. And then you have a cooling system. The basic idea is that all the NMR experiments are still the same. You can perform the experiment exactly in the same fashion, the redo or CP or the respiration CP. Only thing is that throughout the experiment, the microwaves will be on and the experiments will be at low temperature. But remaining all the theory and the interpretation of the data will remain the same. So here is an example, and that you probably have seen, but now probably it fits better with the context, that if you record the CP spectrum on the dry proton phosphorus, on the dry PSPP sample, then you see without DNP, without these turning the microwaves on, this is the signal that you get in 22 minutes. But when you turn on the microwave, the signal becomes significantly more intense, and it takes 40 seconds to record this kind of signal to noise ratio. So that's a huge improvement in sensitivity. And that allows you to perform the more advanced experiments like we use this to do respiration CP. But now I'll talk about how do we perform the homonuclear dipole coupling experiment, because those were difficult due to the sensitivity, but now we have DNP. So now let's discuss about the homonuclear recoupling. So here homonuclear recoupling, the idea is basically similar to what there was in Rideau. You put the pi pulses at every 1 rotor period in this case. The idea is similar, but the mathematics is significantly different from Rideau, and it requires both chemical shift and the heteronuclear dipolar coupling. And I don't think there's any point in going into the details of the maths, but the basic idea is that again, you get a homonuclear dipolar coupling information in your Hamiltonian, which is dependent on the relative distance of, for example, phosphorus and their orientation. So this kind of experiment usually can be performed in 2D fashion. So here is an introduction to the 2D. So basically what we do now, because we do DNP, and DNP enhances the proton, and now we transfer those protons to phosphorus. So X would be phosphorus in this case. So the polarization at phosphorus is huge. And then we put a delay. And during this delay, phosphorus chemical shift will evolve. After this delay, we put the magnetization back into the Z direction and do RFDR mixing. And we have a control on the mixing time of RFDR. And then we record the signal. So basically, just like the heat core, you have 2 dimensions, but in this case, both the dimension will correspond to the X channel, which is phosphorus in this case. And the spectrum will look something like this. So here, let's see this model. In this case, now all 5 belong to same I spin. And in this case, you see that there will be peaks at diagonal because I spin will evolve in this as well as this dimension. So for example, the chemical shift of I1 will evolve in the indirect dimension as well as direct dimension, and those will be at the cross peak of omega 1 cross omega 1 being the frequency of chemical shift of I1. So these peaks basically are non-informative because these basically are the 1D peaks. Those are evolving in both the cases. However, the cross peaks are the interesting ones because those peaks are coming, for example, this peak here is at the peak omega 1 in the direct dimension, but omega 3 in the indirect dimension. This means this peak was evolving with the chemical shift of omega 3, I3, and that got transferred to I1 because of this strong coupling during this time. So the stronger the coupling, more will be the transfer, higher will be the peak intensity in this contour plot. So that's how you can interpret these peaks. So for example, here you see a cross peak at omega 1 cross omega 3. You see a relatively weak peak at omega 1 cross omega 2. And that's because now the coupling between 1 and 2 is weaker compared to coupling between 1 and 3. So that will result into the weaker peak. So now let's see a practical example of this, and that we did in our same PSPP sample. And so here is a dry PSPP sample and RFDR spectrum using the sample sequence. First transfer from proton to phosphorus and then use Rideau to transfer from one phosphorus to another phosphorus and record. And here are the peak assignments. So you see there are diagonal peaks on these dashed lines. And those peaks are non-informative. Basically, this is the Q3 sideband, this is the Q2 peak, this is the Q3 isotropic peak, things like that. But if you see these peaks, those are not on these dashed lines, those are the cross peaks. For example, this one, which is located at Q2, minus 25, around minus 25 ppm, and Q13 star, which is around 0 ppm, because you see from the CP that the sideband of Q3 was around 0 ppm. And this cross peak is a confirmation of existence of Q3, Q2 kind of linkages. Similarly, you see these cross peaks as well, confirming that there are Q3, Q2 linkages present in the sample. These kind of polyphosphates are present in the sample. Now you can do the same experiment in slightly hydrated state. So this was exposed to water or air exposed for a few minutes and then recorded the spectrum. And now we start to see, in addition to these Q3, Q2 correlations, these Q1, Q2 correlations marked by the star or the red circles here. Because for example, this is Q2 in this dimension around minus 20 ppm. And oh, sorry, this is not the right peak, but you should look into the peaks, for example, here, which is Q2 cross Q1, because this is Q1 around minus 11 ppm in this dimension, and Q2 around minus 28 ppm in this dimension. So this is the confirmation of Q2, Q1 peak. So this is confirmation of these linkages in addition to the Q3, Q2 peaks that appear. So these kind of information can be obtained using these RFDR experiments. So now we have covered the homonuclear correlation spectroscopy as well, and its practice. I see. So now we have seen the homonuclear correlation spectroscopy in this case. But if we have time, or if you want, we can go into double quantum, single quantum. If you have questions, you can ask here. Stavros, tell me if I should continue.
Yeah, I don't see any hands raised. You should, yeah, you could continue.
Yeah, it's already 1.5 hours, so probably people are a little tired. Okay. So now let's go for the double quantum, single quantum experiment. And that's the last topic of today. And it's basically homonuclear, but the basic idea is you can now find a pulse sequence that recouples the homonuclear coupling, just like RFDR. But instead of using pi pulses, you use pi by 2 pulses with 2 different phases. So the pi by 2 pulses with 2 different phases gives rise to slightly different Hamiltonian. Instead of 0 quantum, it's double quantum. And what do I mean by double quantum? Is simply that if there are 2 spins, you see there are 4 levels, and there is this kind of double quantum transition that occurs in these kind of, in presence of this Hamiltonian. Now this is very specific transition, because this transition happen, of course, only if the 2 spins are coupled. So just by looking at any peak in this case will give you directly the information about the coupling strength of the two spins, and this will become clear in the next slide. But one should note that these coherences are relatively faster relaxing, so that's a time costly experiment, because the sensitivity is low because of the more effects of relaxation times. And you will see in the next slide that the frequency, the bandwidth requirement is higher, and that means it requires more points in the indirect dimension. So let's see how these experiments are performed. So basically what you do is you use these BABA kind of pulse sequences to excite double quantum correlation. And at the end of this pulsed block, you have a double quantum coherence and let it evolve under the T1 time. And then you use the same pulse sequence to reconvert it to single quantum and detect it. So then what will happen, let's take the same model of the 5 spins. Now in this case here, the coherences will evolve if the I1 and I1 coupling, I1 and I1 both, they have same chemical shift. But if they are clustered, they have 2, then there will be at twice the chemical shift frequency, 2 omega 1. So in this case, the diagonal peak at omega 1 cross 2 omega 1 is not non-informative, but it tells you that there are 2 similar phosphorus species that are coupled, that are clustered. So for example, here I2 are strongly coupled, and that would lead to a strong diagonal peak. Whereas there is only one I3 that will give you almost non-existent omega 2 to omega 3 peak. So the diagonal peaks tells you the clustering of the similar species. Now, if the species are coupled, for example, I1 and I3, then during this time, the chemical shift will be the summation of the two, I1 and I3. So omega 1 plus omega 2, omega 1 plus omega 3. And in this dimension, it will be either omega 3 or omega 1. So you will get these kind of peaks. So this is way more well resolved because the gap between the frequencies in this dimension is more because of the addition of the frequencies. However, these experiments are more difficult to perform, especially if your system is fast relaxing. And the chemical shift range, so the spectral width in this dimension is large. It's twice compared to the single quantum correlation spectroscopy, and that would lead to, that would require a more number of points in this dimension. And that means your experimental time will be significantly longer. However, in certain cases, these experiments are still worth doing because the information is really unique. Okay, so that's all I have, and I'll summarize this part. Basically, I told you that the dynamic nuclear polarization can be used to perform NMR with high sensitivity, and that will allow you to do more advanced experiments. For example, RFDR that we performed. We also performed DCP that I did not show today using the same sensitivity enhancement. The homonuclear correlation spectroscopy can provide you the detailed information about phosphorus correlation in this case. And then you see there are possibilities of these more advanced double quantum, single quantum experiments that we can perform in future to get more detailed information of the clustering of the similar kind of spins. And of course, there are way more number of experiments that exist. And I did not include all of them because I thought it will be way more technical and probably overwhelming. But I clearly see that I underestimated the flow because I thought this will take 2 hours, but it took 1 hour and 1.5 hours. So if you have questions, feel free to ask, else I saved you half an hour of the day.
Thank you, Sheetal. Mateus?
Yeah, so one question, maybe you mentioned it, but I missed it. So you mentioned before that the cross polarization you cannot quantitate because you are a little bit biased.
Yes.
What about all these? So does that also hold for all these other experiments that you were talking about? All those experiments, essentially all those experiments that involve some sort of transfer.
Yeah. So I should be more precise in when I say you cannot use it quantitative. You cannot use it quantifying the amount of the species. But if you are quantifying the correlation, if you are quantifying, for example, how many Q3 or how many POSI linkages are present, then actually that's the information that you are getting from SIOP correlations. So the phosphorus spectrum that you get after the SIOP, that phosphorus spectrum you cannot use to quantify how many phosphorus is present in the system, but that will tell you how many phosphorus are present that are linkages to, that are involved in SIOP linkages. Of course, for that you need a reference, directly phosphorus spectrum. And of course, for that also there are technical details because when you do SIOP correlation, do you 100% transfer? So then you need to scale down and all those things. But in principle, it's possible to quantify what's the percentage of SIOP, what's the percentage of phosphorus species that are present in SIOP linkages. But the quantification can still be very complicated because the involvement of the factors of relaxation times and the performance of the experiment.
I see. And I had another question, just curiosity. Are you planning on doing the double quantum experiments on these P materials to see the nearby phosphorus?
So that we attempted, that we wanted to see if there is pyrophosphate, because then both the phosphorus are similar in chemical shift. But this is one of the systems which is slightly complicated for these kind of experiments. As I mentioned, that these experiments are more demanding in terms of experimental time and also more sensitive to the relaxation times. So we did not get the double quantum, single quantum spectroscopy. And that does not tell us that the pyrophosphate didn't exist. It could be worth trying on some more model systems. We tried on carbon model system, amino acids, and there we see these double quantum, single quantum peaks as we expect them to, but we did not see on the PSPP. However, we cannot use that as a conclusion. Basically, that's my point, because these samples are fast relaxing. So non-existent peak does not tell that these correlations do not exist.
I see. Thank you. That was a great talk, actually.
Yes, Songi.
I have a follow-up question on that. So with the phosphorus, basically that short T2 is the biggest problem, and that among others comes from the material being, of course, more heterogeneous and having multiple species. So can it help if DNP can be done at much faster spinning frequency? We don't have such instruments at UCSB, but you know, there are some development where supposedly 40 kilohertz can be done with DNP. Would that enable multi-quantum phosphorus NMR?
I think that will help, because the efficiency also, so there are these pulse sequences, and efficiency of these pulse sequences sometimes, not more, all the times, but sometimes improves with the spinning frequencies. Mm-hmm. If you get the required power. So one difficulty with going into higher, faster spinning is that power requirement may go higher. Mm-hmm. But with these instruments, I think those powers are available. And then if you can perform these experiments, I think double quantum, single quantum will work.
Mm-hmm. Another question is for the RFDR phosphorus, do you need absolutely DNP? Can that be done without DNP? Because if you do, then you can go to higher temperature, and then the T2 will be longer.
Yeah, I wish that could be done without DNP. The thing is, DNP helps a lot in this case. So it seems that with DNP, that experiment takes only a couple of hours or 3 to 4 hours. But without DNP, it will still take several days, because 1D spectrum takes at least half an hour. And if you go to higher temperature, it will take even longer time. So I doubt that. And also CP doesn't work. So this sensitive CP doesn't work without DNP in these experiments. Okay. And, yeah.
No wonder people weren't so clear about the multiple phosphorus and phosphorus silicon connectivity in real sample. Those are very difficult experiments, huh?
Yeah, so those are actually most commonly done on phosphorus, actually, those double quantum, single quantum, but in really well-defined samples. If you have crystalline phase, or also in solution state NMR, similar experiments exist, but in the samples with the kind of heterogeneity, it's not.
Yeah, or in bone materials. I've seen that in biomaterials in bone, where you have polyphosphate, ACP called amorphous crystalline phosphate or something like that. I have seen multi-quantum NMR done to see how many clusters of phosphorus are connected to each other.
Yeah.
We have a question from Tadnuma. I hope I pronounced your name right.
Yes, you did. Thank you. Sheetal, so I was thinking about the samples with the higher phosphorus content. So one of the reasons, I guess you mentioned, that we don't see efficient double quantum, single quantum is because of the large CSA. But in the higher phosphorus content samples, we see lower CSA. Do you suspect that for those we will see more efficient quantum single quantum?
Yeah, so there, so that's also in hydrated samples. So we attempted this. So this is a really good point. We attempted this double quantum, single quantum only in dry samples.
Yeah.
So after hydration or after water exposure, these relaxation times elongate. So we can perform actually, and we can attempt actually. I don't know what will be the result, but we can perform. Also, the good point is that the CSA becomes less. And CSA is a contributor to fast relaxation time. So under those conditions, maybe double quantum, single quantum are worth attempting.
Okay, yeah.
We have time for more questions.
I have one question.
Sure, go ahead.
So I'm someone who does not do application of NMR, does not do much application of NMR. Suppose someone comes to me with a sample and asks me, oh, can I get this information? And the experiments can be very long, but are there some simple experiments one can do and quickly test if a more complicated experiment would be possible or not?
Well, okay, so that's a broad question, but usually, probably you really know well it as it, but still, I think what you would do is you would first record the simple 1D spectrum, line width, and the relaxation times, because that already tell you what kind of sensitivity you can expect in more advanced experiments. So it's always worth doing the relaxation time measurements before going for more advanced experiments.
Like in T2 measurement or?
Yeah, so T2 you can directly extract from the line widths, but you still worth doing spin-up experiment as well as the T1 also. For example, the CP, in this case, for example, we did direct phosphorus NMR at 800. And then we attempted CP, and to our surprise, CP didn't give us any signal. It was really insensitive. And it turns out that in the dry sample, the protons are really less in amount, and those that are present are not close to the phosphorus sites. So even the CP didn't work. So there was no point in going for correlation spectroscopy afterwards, because by direct excitation, the sensitivity was simply too low. Also, if you do direct, you know that the phosphorus has way longer relaxation time. That means that the recycle delay between different scans is long. So experimental time goes exponentially high. Not exponentially, but significantly high.
So for example, if I can get a 1D in a minute or 2 minutes, then 2D would be like that multiplied by the number of dimensions in the indirect dimension, number of steps in the indirect dimension.
Yes, roughly. Usually you still need more scans, but roughly that gives an estimation. So for example, if 1D take 8 scans, a 2D may require 32 scans because you lose some sensitivity in polarization transfer and some relaxation. But yes, if the 1D is in 1 or 2 minutes, then it's definitely possible to do a 2D. Most likely it's possible to do 2D in few hours.
Mm-hmm. And is signal to noise ratio in the 2 dimensions are same or different?
Yeah, so the signal to noise ratio depends on your number of scans, of course. In 1D, you use a particular signal to noise ratio, and then in 2D, you first can record a 1D version of a 2D, just one delay, and record a 2D, and that will tell you that how much you are losing of your signal because of different transfer efficiencies and different relaxation times. And then you can optimize your number of scans to get the desired signal to noise ratio and then perform the 2D experiment.
Mm-hmm. Okay.
Okay, so Yeah, if there are no more questions, we think.
Well, yeah, I'm not sure. Yeah, yeah, I don't see any more hands raised.
Yeah.
So thank you very much for your time, Sheetal. It was a great seminar. Probably I could unmute everyone to give you a hand.
Thanks.
I'm not sure that I can do that. Thank you. Thank you very much. Thank you very much. We appreciate your time, Sheetal.
Thank you.
Thank you.